Hello, welcome back. We are now on to the fourth section of our Regents review. And this one's all about math and math, chemical equations, balancing equations, and of course, you can't talk about any of that without the dreaded moles. So, let's get into it. The first thing that we really discuss, and it's kind of an overarching thing throughout the entire year, is that all chemical reactions have three things: mass, energy, and charge that are conserved. Meaning they don't change from one side to the next. And so whether that energy is stored in bonds or if that energy is resulting in temperature, it's going to be the same on both sides of the equation. Mass kind of, refers to types of atoms, and charge is obviously plus or minus, stays the same. So what I always like to say, and it doesn't kind of, unless you understand everything that we just talked about, this won't make sense. But reactants have to equal the products. They can be assembled in different ways. They can have different temperatures. But all in all, everything about them, mass, energy, and charge, has to be the same. And these laws, well, each of them have their own law of conservation of mass, law of conservation of energy, law of conservation of charge, right? But specifically the one that comes up a lot is talking about the law of conservation of mass. And every chemical equation demonstrates it because you have to have the same number and the same type of every atom on both sides. So if we take a look at this example, one of the things I always teach my students how to do is draw a line down the reaction arrow. And I ask them to do this because it helps them see the difference. These two sides have to be the same in terms of makeup. They can be arranged differently, but they have to have the same makeup. So if we just kind of went through this, right? I know it's easy to see, but there are two H's here, and there are two H's here, and there are two oxygens here. So this brings us to a grand total of 4 hydrogens and 2 oxygens. Now this right side has to have the same exact situation. It just doesn't have to be arranged in the same way. And what do we have? 2 H's and 1 oxygen. 2 H's and 1 oxygen. And that brings us again to a grand total of 4 H's and 2 O's. So we have completely different things. We have hydrogen gas and oxygen gas on the reactant side. We have 2 moles or 2 molecules of water on the right side, but we didn't change the ingredients from the start to the finish. Okay, and this is the law of conservation of mass. In Regents chemistry, we kind of demonstrate these different types of equations in 5 different types. The first one would be called single replacement. This is when a single atom replaces another atom in a bond. And so the best way to really kind of explain these is to look at the picture down below. Okay? And what we see is A and B are in a bond together. C is by itself. As the reaction takes place, there is a single swapping occurring where C is going to enter into the bond where B was and kick B out into the curb. And that's exactly how this product is created, by singly replacing one atom. If there's a single replacement, there's a double replacement. This is when 2 atoms switch places. And it's the same concept as before, where we have A and B, and we have C and D. And in this process, C is going to swap with B again. But because C was already in a bond, when B switches places, it in turn is also replacing C. Right? Back up here, C was taking the place of B, but B was being left all by itself. In this case, C is replacing B, but B now goes and replaces where C once was in a bond with D, creating two new products of two compounds, and this is called double replacement. Synthesis is exactly what it sounds like. If you've ever played video games growing up, there's lots of types of games where you have to synthesize new equipment or synthesize better defense systems or something of that nature. It's when you're taking different materials, and in this case of chemistry, we're taking atom A and atom B, which are separated, and we're synthesizing them into one main piece. That is synthesis. And the opposite of synthesis is decomposition. Which is breakdown, right? Decomposing happens in nature all of the time. It's literally when you take something that is whole and break it into its separate pieces. And the last one that comes up is combustion or fire. And fire needs to have oxygen. Oxygen has to be a reactant, and CO2 and H2O are always the products of a combustion reaction. So it's important you can identify those things in a chemical equation, because if these are the products and O2 is a reactant, you know you're dealing with combustion, right? It's very specific, unlike these other three where we can replace A, B, C, D with any elements we want, as long as they bond. All right, so let's move along. The next one that we talk about here is gram formula mass. So now we're getting into the math part of it. Gram formula mass. And this is the mass of a molecule when you add up all the elements' atomic masses. So, and I'll keep the numbers simple with whole numbers right now. I won't use any decimals. H2O. H2O is made up of H, and it's made up of O. Okay? H2O is made up of H, and it's made up of O. Switch this color for a second. Because the mass of every hydrogen atom found on a periodic table or your reference table is 1.0, and the mass of every oxygen atom is 16.0. I said I would do whole numbers. I'm still putting a decimal, but let me erase that. Keep it simple. Okay. This orange is the mass of each individual atom. Now what we need to do, because this molecule is not made up of just one of each thing, we're going to multiply this number by how many of each atom we have. So H2O has two H's, H2O has one O. When we add up the components, we find out the little pieces. All of the hydrogen has a mass of 2. All of the oxygen has a mass of 16. Leading the whole molecule of H2O to have a mass of 18 AMUs. Okay, this is the way I kind of do it. It's a lot easier if you're asked to do percent composition at this point, which is something that does often happen. You have the individual hydrogen mass, you have the individual oxygen mass, and then at that point you could just do the part over the whole and times 100, and you would get your percentage of an element within a molecule. Okay? So moles, right? Gram formula mass is the mass of, the elements, but really, because it's gram formula mass, it's the mass of 1 mole. So the mole, or a mole, is the gram formula mass. Formula mass is what is equal, not Z, but is equal to 1 mole mass. So for water, 18 AMUs, this is the mass of 1 molecule. For water, 18 gram equals 1 mole. And a mole is just a quantity. It's just a certain number of particles. Just like 1 dozen is always 12. It could be a dozen pencils, a dozen basketballs, a dozen donuts, a dozen bagels. It always means 12. 1 mole is a specific number, 6.02 times 10 to the 23rd, number of particles grouped together. Okay? We can use the formula for moles that is on our reference table. So and then we're going to write that down as we answer this example. How many moles are in 60 grams of H2O? Well, according to the reference table, moles is equal to a given, which I do not like that term, and I'll explain why, over the gram formula mass. That says GFM. Okay, GFM. And I don't like the word given because the word given is not always, it's not always given to you. In this question, it is given, but I prefer to think of this as the sample mass, or the mass of the sample. And then we just kind of plug it in. So in order for you to solve for moles of anything, you have to know the gram formula mass. And you're always going to know the gram formula mass because you will always be given the molecule that you are dealing with. So for this question, we want to find the number of moles. Well, that's going to be equal to 60 over 18. And 60 over 18, excuse me, is going to come out to 60 divided by 3.33333 repeating moles. Okay, and so if I had 60 grams of water, that would be 3.3 specific bundles, specific packages, specific number of water molecules. Okay, and the last thing that we talk about in formula math, or at least the last thing that we need to talk about, because there are lots of other things that we are going to not discuss on this video. Stoichiometry is the second thing that we have to do with moles. Okay, and what we have to remember from the beginning of the video is that a balanced equation has the lowest whole number ratio. Okay, and it's balanced. What I have on the left, what I have on the reactant side, has to be equal to what is on the right, the product side. The number of molecules, the number of atoms, the whole total mass, everything has to be the same, except for its configuration. Now, it's basically telling you that a chemical equation is a recipe. Right? And in any recipe, I'm going to just make a ridiculous one here so you understand. 2 eggs equals 12 cookies. And that's how I make 12 cookies. Right? I just need 2 eggs. We know that that's not real, but just follow me. If I wanted to make 24 cookies, that would be double the original amount of cookies that I had. Well, I would need to double the amount of eggs that I had. Right? Or if I had 1 egg, that's all I had in my pantry, and I really wanted to make cookies. Well, I couldn't make 12 eggs with 6 cookies. Right? But since 1 is half of 2, I can produce half the amount of cookies with half the amount of starting ingredients. So if I take a balanced chemical equation and I double something, all the other molecules, mole ratios, mole numbers, are going to be doubled. So let's take this example right here. We've been working with water, so let's keep working with water. Okay? We already explained why this is one of these and 2 of these will always give us 2 moles or 2 molecules of water. So what do we do with this? Well, we read the question, and I'll show you how I go about answering these. And I'll use a fancy purple. Okay? So, using the balanced chemical equation, how many moles of water, see, so what I do is I will underline the things that the question is asking me to look for. So it's asking me to look at how many moles of water, and then I will circle it in the equation so I don't get confused. Form if 5 moles of oxygen, so I'm going to be dealing with oxygen here, I'm going to change that 1 to a 5, reacts completely with excess hydrogen. Right? And excess hydrogen means that for this question, that is not important. I want to know if I change my 1 to a 5, how many molecules of H2O are we going to have? And if I set it up like this, well, I read the question like that, you can turn this very difficult thought process into a very simple ratio. Right? And it's that I started with 1 and now I want 5. This is going to equal, well, if I start with 1, I normally end up with 2, but now I want to know how many I'm going to end up with instead. Cross multiply and divide, and what you would find out is that if I start with 1 mole of O2 and end up with 2, and I change that 1 to a 5, my 2 would then create 10 moles of H2O. So those are the most important and basic things that you need to know about stoichiometry and chemistry math. Some other things that we didn't really talk about, density, that comes up in here. Hydrates, that's another thing that comes up in here. Oh, we will talk about significant figures later, so that will come back up. But there you go. I really hope that this video helped you with your chemical math. I know it's just a brief overview, but hopefully it'll start bringing back some memories. Whether they're good or bad, hopefully they can turn to be good. Well, thank you very much. Thank you for watching the video. Like the video, subscribe, and I will see you in the next video.